Hello, and thanks for being with me here today. My name is Rich Pauloo, and I'm a member of the team Function Water Data Science. We're a team of researchers from UC Davis and the Public Policy Institute of California, and we're proud to present our project entitled Domestic Well Vulnerability to Drought in California's Central Valley. Today I'll take you through the analysis, some information for vulnerable communities, a bit about the project, some supporting materials in the appendix, as well as the source code for this project. And I'll aim to do so in about 10 to 15 minutes. So just as a note, I will not be reading all of the text on these slides, but I encourage you to go to this web page where you can view these results and flip through them for yourself for a more detailed walkthrough. So let's begin with the background and motivation. And that is quite simple. It's simply that California's Central Valley is a very dry place, and it's very dependent on groundwater. It's also home to nearly half of the state's domestic well-reliant individuals. And during the last drought from 2012 to 2016, the state received nearly 2,500 domestic well failure reports. The majority of these reports came from places in the Central Valley, and sites like this were not uncommon. Hundreds of thousands to more than 1 million Californians rely on their domestic wells for drinking water, and that motivated our team to answer the following questions. Number one, how will a future drought affect domestic well failure in California's Central Valley? Number two, are well failures more associated with particular social drivers of vulnerability, such as income? And lastly, can we use machine learning models to explain the climatic drivers of domestic well failure and figure out what the well failure probability is for areas in the Central Valley where we do not have data? To begin, we built a spatial model driven by open data from the Department of Water Resources to assess the vulnerability of domestic wells in California's Central Valley. Now, what we're looking at in these panels, we'll start with the panel on the left, is the location of monitoring wells used to gather groundwater level information in the Central Valley. These measurements represent the shallow, unconfined system to semi-confined system. And you can see that we are taking measurements seasonally, so in the spring and in the fall, during the same time window that the drought took place. In the middle panel, you're looking at the interpolated groundwater level from these measurements. Blue indicates a more shallow water table, whereas red indicates a deeper depth to the groundwater level. And on the far right panel, we're looking at the 65,000 or so domestic wells, the locations of those domestic wells, which were cleaned and obtained from the online state well completion report database. The spatial model is quite simple. It looks at the position of all these domestic wells, as well as the maximum groundwater level change during the drought. And it asks the following question. Does the groundwater level during the drought ever fall below the level of the pump in these domestic wells? If it falls below the level of the pump, the well goes dry. If it doesn't fall below the level of the pump, the well does not go dry. You can imagine that shallow wells are more vulnerable to drought and groundwater level change than deeper wells. And that's depicted in this conceptual model right here. So in this conceptual model, we have a blue groundwater level that's falling. And as it falls, if it falls below the level of the pump, represented by these circles here, then the well goes dry, which we show in red. Otherwise, it doesn't go dry. And that's pretty much it. We can look at these modeled results for the 2012 to 2016 drought. And the numbers actually line up with what we observe in terms of well failure reports to the state. We see about 2,500 domestic well failures in the Central Valley, most of the impact experienced in the Tulare Basin. And this is an interactive map which you can play with online that shows you the failure ratio. So the total number of wells that failed in the Kings Basin was 644, divided by the total number of domestic wells, which is 4,732. And we can see that about 13% of wells in the Kings Basin, domestic wells in the Kings Basin, failed or went dry during the 2012 to 2016 drought. We also can look at metrics like just the raw count of domestic well failures, the density of domestic well failures, and the locations of the actual wells themselves. So here we can turn on the wells in the model and see exactly where these wells are failing. So for instance, here it looks like this well is dry, and this well in red is dry at a pump location of 86 feet, and this well was not dry, had a pump location of 162 feet. So in between these two wells, the groundwater level during the drought must have been between 86 feet, greater than 86 feet, but less than 162 feet. And of course, we can zoom out and we can look at other areas, but we're going to move on. In terms of socioeconomic impact, the 2012 to 2016 drought affected income groups disproportionately. Now what we did is we looked at all the failures, these are reported well failures, during the 2012 to 2016 drought. And we classified each of the well failures according to their median household income, which we obtained from the US Census Bureau. We created three categories. This MHI plus category, which we're showing these box plots right here. So the MHI plus category was the median household income or above. DAC was disadvantaged communities at 80% of the median household income in California. And SDAC were severely disadvantaged communities, which were 60% or less of the median household income in California. These box plots show the distribution of distances from each failing well in that income group to its closest water system. Now what that means is that for severely disadvantaged groups, you can see that the interquartile range and the median distance was less than, the median distance is less than 1 mile. So more than 50% of severely disadvantaged communities across the board in all of the Central Valley were less than 1 mile away from their closest water system. This is good news if we are thinking about how to hook people up to water when they have well outages during drought. For disadvantaged communities and median household income and above, the median distance was closer to 1.5 miles, but you can see they have a higher interquartile range at greater than 2 miles at the upper bound. And of course we have outliers in each group, and these are people living in more rural areas that are quite far away from public water systems. Another interesting finding from this simple spatial analysis was that about 1.5 times more well failures were reported by households at the severely disadvantaged level and disadvantaged level compared to the median household income and above. And that's just shown right here. So the count of well failures in disadvantaged and severely disadvantaged communities was about 1.5 times more than those in the median household income and above. Moving on, we can look at future droughts. So we're looking at 1, 2, 3, and 4-year droughts. 1, 2, 3, and 4-year droughts. In terms of their point pattern, so these are the locations where wells failed during those droughts. And these are those well failure counts aggregated at the Bulletin 118 subbasin level in terms of the density, or the number of wells that fail per 100 square kilometers. More yellow means more well failures. And these droughts were created by looking at the 2012 to 2016 drought and simulating 1, 2, 3, and 4-year droughts by scaling that 2012 to 2016 drought. So this 4-year drought that we're looking at, this simulated 4-year drought, experiences a groundwater level change similar to that observed in the 2012 to 2016 drought, which is quite a bad drought. One thing that pops out is that given another 4-year drought beginning the simulation at January 2018, we observe almost twice the amount of domestic well failure as we saw in the last drought, which remember was around 2,500 wells failing. So another 4-year drought that began on January 2018, would give us about 4,000 well failures. And this is because groundwater levels are already low. So future droughts will be more detrimental to domestic wells when that groundwater level is already low and it doesn't take much more to make wells go dry. A future 1 to 4 year long drought would affect income groups more or less the same, we found. And so that's what we can observe here. This is a 1, 2, 3, and a 4 year drought. A 1, 2, 3, and a 4 year drought. These are the point patterns of the well failure, stratified by income level. So the different colors represent. And we can see the median distance from the closest water system for all groups is more or less, it looks quite similar. And they tend to be all less than 2 miles away from their closest water system. Again, we have outliers. And again, this will vary on a county-wide level, which we have in some supporting analyses. This is just a global trend across the Central Valley. Even though these groups may look similar in terms of their distance from their closest water system, we know that these groups will differ in their ability to cope with well failure, which bears a financial burden. Lastly, we used machine learning to assess the climatic drivers of well failure. So in this interactive map, we can zoom into different areas. The failure probability here is shown in red. So an area that is more red has a higher probability of failure. And in the upper right corner, we can look at the failure probability of each raster cell. So the way we did this was we trained an ensemble machine learning classifier on 56 climatic and geologic variables to predict the present-day well failure across the Central Valley. And then we took our climatic information for areas across the Central Valley and we predicted the well failure probability in those areas where we did not have data. And what we found by looking at variable importance was that well failure is mainly predicted by a few variables. Those include the maximum temperature during the summer months and the months that border summer, as well as higher temperature in the spring, fall, and summer, and the swings in temperature. So the variations in temperature at monthly levels, at seasonal levels, and at the annual scale. Precipitation, we found, was not as important a predictor, which makes sense because the Central Valley's water budget is mainly driven by imported surface water, irrigation, and pumped and reapplied groundwater rather than precipitation. So if we were to zoom into one of these cells like so, and try to figure out the failure probability in that area, we can change the base map here to a street map and see an area like Porterville with a failure probability of around 78% that we would observe well failure in this location. So this heat map gives us a sense of what areas are vulnerable, climatically vulnerable to drought. And that is our analysis. Moving on to the next big section, we included some resources for vulnerable communities that include ways to get in touch with your local Department of Environmental Health, information on nitrate for domestic wells, since domestic wells are not tested for water quality in the state, or wells that service less than 5 connections are not tested for water quality. We included information on how to report an outage to the state, as well as financial assistance programs, and lastly, information on how to locate your nearest water system. Here's a bit about the project, including our future directions. We anticipate to write 3 papers covering these topics, which I'll let you flip through at another time. We would like to acknowledge the West Big Data Hub and California Water Data Summit and Argo Labs, as well as some folks that were very instrumental in helping us with data needs. Lastly, you can find descriptions of the data in our appendix, as well as some more particular information on the approach, some supporting analyses, as well as the code, which you can access via this link. I've already opened it here, and this is our GitHub. And in the GitHub, you'll find all of the code used in the analysis in this folder, and all the code used to generate the presentation in this one. Thank you for your time.